So detection methods. We're going to, I think we're going to finish this part before we take a break. So largely, we can categorize outlier detection methods into two groups. One is using supervised methods when you have user-labeled examples. One is not, without training examples, you use other things based on certain assumptions, heuristics about normal and outliers to detect outliers. We can use statistical methods, proximity-based methods, and clustering-based methods. So outlier using supervised methods is like we just mentioned, we can treat outlier detection as a classification problem. We can, there's two classes. One is normal, another is outlier. If we have enough of outliers labeled. And then we learn a classifier. So here the issue is we have an imbalanced class problem. We know that we can use, oversampling and undersampling methods. Maybe we can use other ways to lower threshold and all that. But we have seen in our little exercises that their performance is just, better than not having them, but it's certainly not solving the problem entirely. When we're dealing with a minority class issue, like we also mentioned this before, maybe it's a good time to repeat this, is our goal is to catch as many outliers as possible. Therefore, recall is more important than accuracy or precision. So the goal is to avoid mislabeling. The goal is we don't care about mislabeled normal objects as outliers. There may be non-outliers being included as outliers, but we want to have a chance to individually examine them. In terms of fraud detection, for example, you want to have a better recall, so you're not letting go of those fraud incidents, but you can then add in using human experts and other human resources to verify those events. So recall is more important than precision. Using supervised methods. Unsupervised method, the basic assumption is that the normal objects are somewhat different from outlier. By definition, outlier behaves differently from normal objects. So we assume that this is an okay assumption that normal objects are somewhat clustered. And the outliers are far away. This assumption may or may not work for collective outliers, but later on we're going to talk about collective outliers. Because the collector outliers may share, may be clustered, actually very densely clustered in a small area. So with knowing the existence of collective outliers will help you to see that clustering some small clusters may actually be outliers. As you can see that many clustering methods can be were already designed and can be adapted for outlier detection. For example, the density-based methods, the Danclu methods. But again, there is challenges, noise from outliers, and also cost may be something to consider. When you using cluster method to detect outliers, as the cost issue comes when you actually we know outliers probably are going to be very few, but we actually spend lots of computational power to cluster the entire data set on lots of normal data in order to detect a few, very few outliers that may be, some of the cost may not be necessary. So in this lecture, we're going to cover a few other methods that actually try to find outliers directly. So you don't have to do clustering first. Semi-supervised.
Question.
Yes. Mm-hmm.
So in the previous slide, you were talking here about the density and maybe distance. Which of the two is, like for an outlier, would one say it exhibits distance far away, or does it exhibit density as different?
They could both, yeah. In outlier detection, we use distance-based and also density-based methods to detect them.
And is there a way to combine the two, or?
I think they all, in some ways, are combined. It's just when we label them. For example, when we do density-based methods, we do reachability distance, right? There is a distance measure in it. What I'm saying is you cannot do density without distance, or distance completely without density. You have to look at a data point and its neighbors and also the distance. So semi-supervised method, this is, we know that because label data is very few when we do outlier detection. Semi-supervised methods, they're very intuitive to understand, but the performance definitely there's still a lot of room to be improved. When you have some labeled normal data available, you can use the labeled examples and its neighboring unlabeled objects to train a model and call that model a good model for normal objects. And then you use that model on other objects. Any objects that are not fitting that normal model becomes an outlier. Yeah, the general idea is like this, but the performance is very questionable. If only some labeled outliers available, a small number of labeled outliers, really, I don't think that makes solve any problems, but maybe that's just a useful statement to have. A small number of labeled outliers may not cover the possible outliers out well. Isn't that obvious? To improve the quality of outlier detection, one can get help from models for normal objects learned from the unsupervised method. Well, yeah, forget about that. I don't think that makes sense. There are statistical methods. I'm not going to talk about things on those slides because later on we're repeating the same thing in much more detail, so we don't have to spend time here. Proximity-based methods, here we can use distance-based or density-based methods to find outliers. And we can use clustering-based methods, which basically using existing clustering algorithms to help detect outliers.